All right, so now I'm going to be talking about Lab 2, or reviewing Lab 2, since you just did it. So it's about simple harmonic oscillation, all right, which is essentially when an object experiences a restoring force. So essentially, if you have a spring and you attach, a mass to it, and then you pull this mass away, the spring is going to pull back on the mass. And so that's a restoring force. And so but once that restoring force, essentially it carries the block with it with momentum. And so that momentum compresses the spring past its equilibrium point. And then when it does that, it's going to, the spring is now going to want to push the block forward, right? And then it pushes the block forward until it reaches this point again. And then it just does that endlessly, assuming it doesn't lose energy to like friction or air resistance or whatever. And so that's described by, at least in springs, by Hooke's law, which says F equals negative kx. Again, k is just a constant. X is the displacement of the spring, so essentially how far you've stretched the spring. And then this negative just tells you that it's a restoring force, because if I pull it to the right, then the force is to the left. And if I push it to the left, meaning my displacement would be negative, then the force is now positive and to the right, because k is going to be positive. All right? And so that's sort of the background on Hooke's law. And then really quickly, I'll talk about this equation. So this is the equation you were sort of using in the lab when you had just a mass on the spring. So if we put a mass and we attach a spring to it, and it's vertical, then if we were to draw a free body diagram for the mass, there's going to be some mg force down, and then you've stretched the spring down, so now there's a kx force up. All right. And so that's sort of what all this equation is saying, because if the spring is no longer accelerating, meaning like the spring is stationary, then this will be the case. All right. And so, then it goes into this derivation of the general form of the displacement, but that's not super important. I think what, like understanding the derivation is not super important. I think you should understand it, but it's not like necessary for the LSA. It might be more necessary for the exam and the lecture exam. I'm not sure. I don't know what the lecture exams look like, but essentially you get this general form of a wave in simple harmonic motion, and then this omega is the angular frequency, which is 2 pi times the frequency, and then the frequency is 1 over the period of oscillation. And then this happens to be equal to the square root of the spring constant divided by the mass. Stuff like this is stuff that you should definitely understand for the LSA, and like having your lab manual, just like knowing equations. Like if you took 40A last quarter, you should have seen that there were several times where like equations you were using in the lab show up on the LSA. And so if you've never taken an LSA at UCR, then equations are pretty important, like understanding how to use them in different problems. And then the period is 2 pi root m over k, which we can find from omega, because we know omega t equals 2 pi. It's given here. You could also just see it. If you change this f to 1 over t, then you could see that as well. Omega t equals 2 pi, and therefore t equals 2 pi over omega, which implies that t is 2 pi root m over k. All right. And so then they tell you that this like fit parameter is 2 pi over root k. I'm going to talk more about where that comes from a little bit later. Then again, I went through this derivation of how the mass of the spring contributes to the energy. Understanding the derivation is not super important. You should understand how to use the equation though. I will talk about really quickly how this comes up. It's not super important, but they find that like k due to the spring, or like the k of the spring, is 1/2 m over 3v squared. And then in classical mechanics, or just like mechanics in general, if you have something of the form like 1/2 times some constant times v squared, you can like put it into like, you can create a matrix, and if you find the determinant of the matrix, then you can like find the you find the determinant, then you can find the eigenvalues of the matrix, and then you'll end up finding this, but that's not important. But just know that's I guess you don't even need to know it, but that's where it comes from if you're wondering. Uh, I'm happy to talk more about it if you want to ask me in lab or something. But you end up doing this experiment with like a weight hanger and a motion sensor, and then you did an experiment, and you were hanging masses and looking at Hooke's law, and so you should definitely understand what you did in the lab relating to like how you fit the equation to find Hooke's law and like stuff like that. And then like, does Hooke's law adequately describe your measurements? I mean, it depends on who it was. Like, for some people maybe it didn't describe it as well as others, and that's okay. Like, that's what experimental physics is about. Then it asks like, how could you adjust Hooke's law model to make it more accurately model your data? This is like a really open-ended question. Like, you could just add on like a constant to say like maybe there's like a constant force because the spring is hanging, and maybe we can model the weight of the spring as like just a constant force added on. Or maybe you could say that like instead of f equals negative kx, like we should take into account that like k is maybe nonlinear, or that k is non-constant, meaning as you stretch the spring more, the spring constant changes. All right, so stuff like that. I think that's what the question was sort of getting at. But then you actually did the simple harmonic oscillation part of the lab, where you put a mass on your spring and then you stretched it down, and then you looked at how far the spring, or how far the mass moved up and down and how long that took, and you applied this fit. And then if you apply the fit, this A is the amplitude of the oscillation, which is essentially how far up and down it's moving. Or, I mean, it's really like if the mass at its peak goes down to like here at its bottom, this is really 2 times the amplitude, because remember the amplitude is the distance from the equilibrium to either peak. All right. And so then you found that T is 2 pi over omega. Again, equations like that are stuff that you want to know for the LSA, in case you're asked a question related to it. And then you fit a y equals a squared x plus b graph and a y equals a squared x graph to your data. And so this is where like the a equals 2 pi over, or sorry, k equals 2 pi over root a comes from. So where it comes from is that this y is really 2 pi root m over k, right? Because what we're really looking at is, if you recall, we're looking at omega, right? Like our angular frequency. And if you remember from earlier, we said that the period is 2 pi root m over k, right? And that's related to omega, right? So you were looking at, sorry, I kind of misspoke. I said you were looking at the angular frequency. I meant to say you're looking at the periods, right? Because in 2.5, you were repeating the previous experiment up to 300 grams, and you were recording omega in your notebook, but you were also recording the oscillation period in Capstone itself. Okay. And so 2 pi root m over k is your period, right? And that's going to be equal to our a square root x. Okay, but remember on your x-axis was the mass. So we change x to m, and then this is equal to a times the square root of m. And so here we have this like pesky 1 over k here that we want to get rid of. And so what happens to be true is that in math, if you have like square root m over k, this is equal to the square root of m divided by the square root of k. And so this implies that 2 pi root m over k can also be written. So it's like equivalent to 2 pi over root k times the square root of m. And here, if we match these two equations, we can see that we can just write a as 2 pi over root k. And then we can say that k is then the square of 2 pi over a. All right. And so that's how you found k from your graph. All right. And then part 3 is about additional questions. So under what conditions is Hooke's law invalid? So it's invalid when, for example, you don't have a constant k. So like if k is non-constant, it's also invalid if if you stretch the spring too far and like permanently deform it. Now the k value has changed. So again, it's non-constant. So that'd be an example when it's invalid. There's certainly other examples you could think of though. And then the next part is like, what is simple harmonic oscillation? So simple harmonic oscillation is oscillation due to a restoring force. So in this example, like in this lab, the restoring force was Hooke's law, which is F equals negative kx. And remember, this negative signifies that it's restoring, because if I push it to the right, it goes to the left. If I push it to the left, the force is to the right. Okay, and then in 3.2, you saw that the amplitude of the spring oscillations decreased over time. What that means is that if you had this, it's going to decrease over time. And so we can actually model this as an exponential decay. So we can say that y is equal to like e to the negative gamma t times your sine. I'm just going to sine of omega t. And so this e to the negative gamma t is our exponential decay. And then this is like specifically, I mean, so like this is in general how you model dampening or damping. I don't think it'll be like on the LSA. I'm not entirely sure. I doubt it, but it could be on the like the lecture final. I'm not 100% sure. But there's different types of damping. So there's underdamped, and then there's also critically damped, and then there's overdamped. And so in this lab, we saw underdamped. And so underdamped oscillation is like when an object keeps oscillating, but it decreases in amplitude over time. And then overdamped is like it doesn't oscillate and it decreases over time. And then critically damped is the other one. And that's when like it reaches the equilibrium point as like quickly as possible, more quickly than overdamped. But in this lab, you're only dealing with this underdamped, where we saw this oscillation and decreasing amplitude over time. And then the last question was like, what would happen if these experiments were performed in a zero gravity environment? So for the first lab, or for the first part of the lab, your spring just wouldn't stretch at all, and then you couldn't really model Hooke's law because we never have a displacement to measure to try to find k from. So the first part of the lab is like genuinely impossible. And then the second part of the lab, it's also impossible, but only because our spring is incompressible. So if you pull, so like when you just let the mass hang, it's not going to move down, right? That's just from the fact that there's no gravity to pull down the mass, so the spring won't stretch out. However, what does happen is, or like what you are allowed to do is pull down on the mass. So we can still pull down on the mass like you did in the lab and then let it go. And so like theoretically, you would think that you would see oscillation. However, when the mass reaches its highest point where the spring is like fully compressed, it can't compress anymore. And therefore Hooke's law becomes invalid once you reach that region, and the oscillation will just like stop. Or it'll like, you'll have like significant damping where like the first time it hits the top, it like the amplitude of the oscillation, drops by a significant factor, like a factor of 10 or something. However, in general, you could have a spring that is like initially spread out. And then if you pull it down, as long as you don't pull it down too far, you can have oscillation in the zero gravity environment because the spring is compressible. But that was really it for this lab. In regards to the LSA, just make sure you understand, where if you took 48 last quarter, there were a few questions that might have been related to like getting values from fits or stuff like that. So definitely understand fits, and also, understand all the equations they used in the lab and, how you would apply them again to the lab. Like if you were to perform the lab again, how would you use the equations to do the lab? So that's really it for this video. Thank you.